The practice of using the high leg, which is 208 volts, and a 120 volts phase to supply 240 volts appliances is not acceptable according to the National Electrical Code. National Electrical Code Section 210.6 B2 states that a 208Y/120 volts, 3-phase, 4-wire system with a high leg is intended for 3-phase and 120 volts loads only. National Electrical Code Section 430.22 requires that 240 volt single-phase appliances be connected using both 120 volts phases of the 3-phase system. There are several reasons for this prohibition. Firstly, using the high leg for 240 volts appliances can create an imbalance in the system which can lead to voltage fluctuations and potential damage to equipment. Secondly, the high leg is typically protected by a larger circuit breaker than the 120 volts phases, which can result in overloading of the 240 volts appliance. Thirdly, if the high leg is inadvertently connected to a 120 volts appliance, it can cause the appliance to overheat and potentially start a fire. Using the high leg for 240 volts appliances is a violation of the National Electrical Code and can result in fines, loss of insurance coverage, and safety hazards. To avoid imbalances and safety concerns, the preferred solution is to encourage customers to accept 3-phase/4-wire, 120/208 volts Y services. For existing 3-phase/4-wire, 120/240 volts with 208 volts high leg services, it is recommended to use the 120 volts phases to supply 240 volts appliances and reserve the high leg for 3-phase loads only. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical wiring and equipment installation in the United States. It is updated every 3 years to reflect changes in technology and safety practices. The NEC is not a law itself, but it is often adopted by state and local governments as part of their building codes. Adherence to the NEC is crucial for ensuring electrical safety and preventing hazards such as fires and electrical shocks. Several specific sections of the NEC are relevant to the proper use of high leg delta services, particularly regarding the connection of single-phase and 3-phase loads. National Electrical Code Section 110.3b states that listed or labeled equipment shall be installed and used in accordance with any instructions included in the listing or labeling. This means that any electrical equipment, including appliances and machinery, must be installed according to the manufacturer's instructions. This is especially important for high leg delta systems, as improper connections can lead to equipment damage or safety hazards. National Electrical Code Section 210.4 addresses multi-wire branch circuits. In a high leg delta system, it's essential to understand how multi-wire branch circuits are configured to ensure that loads are properly balanced and that the high leg is not inadvertently used for 120 volts loads. This section outlines the requirements for identifying the grounded conductor and the proper use of overcurrent protection devices. National Electrical Code Section 215.9 requires that feeders supplying premises wiring systems have ground fault protection of equipment under certain conditions. This is particularly important for large services such as those found in commercial or industrial settings where the potential for ground faults is higher. Ground fault protection helps to minimize the risk of electrical shock and equipment damage. National Electrical Code Section 230 covers services, which are the conductors and equipment used to deliver electricity from the utility company to the building. This section includes requirements for service disconnects, overcurrent protection, and grounding. It's crucial to ensure that the service is properly sized and installed to meet the building's electrical needs and to provide adequate protection against overloads and short circuits. National Electrical Code Section 250 deals with grounding and bonding. Proper grounding and bonding are essential for electrical safety, as they provide a low impedance path for fault currents to return to the source, tripping the overcurrent protection device and preventing electrical shock. This section outlines the requirements for grounding electrodes, grounding conductors, and bonding of metal enclosures and equipment. National Electrical Code Section 408 covers switchboards and panel boards, which are used to distribute electricity throughout the building. This section includes requirements for the arrangement of overcurrent protection devices, the identification of circuits, and the proper labeling of the panel board. It's important to ensure that panel boards are properly installed and maintained to provide reliable and safe electrical distribution. National Electrical Code Section 430 covers motors and motor circuits. Motors are a common load in many buildings, and they can draw significant amounts of current. This section includes requirements for motor overcurrent protection, motor disconnecting means, and motor control circuits. It's important to properly size and protect motor circuits to prevent overheating and equipment damage. National Electrical Code Section 440 covers air conditioning and refrigeration equipment. This type of equipment often requires dedicated circuits and special overcurrent protection. This section includes requirements for the sizing of conductors, the selection of overcurrent protection devices, and the proper grounding of the equipment. It's important to follow these requirements to ensure the safe and reliable operation of air conditioning and refrigeration systems. National Electrical Code Section 600 covers electric signs and outline lighting. These types of installations often involve high-voltage circuits and require special safety precautions. This section includes requirements for the wiring of signs, the grounding of metal parts, and the installation of overcurrent protection devices. It's important to follow these requirements to prevent electrical shock and fire hazards. National Electrical Code Section 700 covers emergency systems. Emergency systems are designed to provide power to essential loads during a power outage. This section includes requirements for the design, installation, and testing of emergency systems. It's important to ensure that emergency systems are properly installed and maintained to provide reliable power during an emergency. The high leg, often referred to as the wild leg or stinger leg, has a voltage to ground that is significantly higher than the other phase conductors. In a 120/240 volts high leg delta system, the voltage from the high leg to the neutral conductor is approximately 208 volts. This higher voltage is due to the way the transformer windings are configured in the delta system. The high leg is typically marked with orange color coding to indicate its higher voltage and to prevent accidental connections to 120 volts loads. When working with the high leg delta system, it's crucial to properly identify the high leg and to avoid using it for 120 volt circuits. Using the high leg for 120 volts loads can result in equipment damage and safety hazards. Instead, a high leg should be reserved for three-phase loads or for specific applications where its higher voltage is required. Understanding the voltage relationships in a high leg delta system is essential for safely and effectively working with this type of electrical service. The 120/240 volts high leg delta service is a three-phase, full-wire system that is commonly used in older buildings and in some rural areas. It is characterized by one phase having a higher voltage to neutral, typically 208 volts, than the other two phases, which have 120 volts to neutral. The high leg is created by center tapping one of the transformer windings in the delta configuration. This center tap serves as the neutral conductor for the system. The voltage between the two phases that are not center tapped is 240 volts. The voltage between each of these phases and the neutral is 120 volts. However, the voltage between the high leg and the neutral is approximately 208 volts. This is because the high leg is derived from a different point on the transformer winding than the other two phases. The high leg is typically marked with orange color coding to indicate its higher voltage and to prevent accidental connections. It's crucial to properly identify the high leg before working on a high leg delta system to avoid electrical shock and equipment damage. When connecting loads to a high leg delta system, it's important to follow the National Electrical Code requirements. Single-phase 120 volts load should be connected to the two phases that have 120 volts to neutral. Single-phase 240 volts load should be connected to the two phases that have 240 volts between them. Three-phase load should be connected to all three phases, including the high leg. It's important to avoid using the high leg for 120 volts loads, as this can result in equipment damage and safety hazards. The 120/208 volts Y service is a three-phase, four-wire system that is commonly used in new buildings and in urban areas. It is characterized by all three phases having 120 volts to neutral. The 120/208 volts Y service is derived from a Y-connected transformer, where the neutral conductor is connected to the center point of the Y. The voltage between any two phases is 208 volts. The voltage between each phase and the neutral is 120 volts. This makes the 120/208 volts Y service ideal for supplying both 120 volts and 208 volts loads. The 120/208 volts Y service is also more balanced than the high leg delta service, which means that the voltage is more stable and less susceptible to fluctuations. This can help to improve the performance of sensitive electronic equipment. When connecting loads to a 120/208 volts Y service, it's important to follow the National Electrical Code requirements. Single-phase 120 volts load should be connected to one phase and the neutral. Single-phase 208 volts load should be connected to two phases. Three-phase loads should be connected to all three phases. The 277/480 volts Y service is another common three-phase, four-wire system that is used in commercial and industrial buildings. It is characterized by all three phases having 277 volts to neutral. The 277/480 volts Y service is derived from a Y-connected transformer, where the neutral conductor is connected to the center point of the Y. The voltage between any two phases is 480 volts. The voltage between each phase and the neutral is 277 volts. This makes the 277/480 volts Y service ideal for supplying large lighting loads and other high-power equipment. The 277/480 volts Y service is also more efficient than low-voltage systems, as it reduces the amount of current required to deliver the same amount of power. This can help to reduce energy costs. When connecting loads to a 277/480 volts Y service, it's important to follow the National Electrical Code requirements. Single-phase 277 volts load should be connected to one phase and the neutral. Single-phase 480 volts load should be connected to two phases. Three-phase load should be connected to all three phases. Balancing the load on a three-phase system is essential for ensuring efficient and reliable operation. When the load is imbalanced, the voltage on each phase can vary, which can lead to equipment damage and reduced performance. There are several ways to balance the load on a three-phase system. Firstly, distribute single-phase loads evenly across all three phases. This means that the total current drawn from each phase should be approximately the same. Secondly, use three-phase loads whenever possible. Three-phase loads draw current evenly from all three phases, which helps to balance the system. Thirdly, avoid using the high leg for 120 volts loads. As mentioned earlier, using the high leg for 120 volts loads can create an imbalance in the system. Fourthly, monitor the voltage and current on each phase. This can help to identify imbalances and take corrective action. Fifthly, use power factor correction capacitors. Power factor correction capacitors can help to improve the power factor of the system, which can reduce the amount of current required to deliver the same amount of power. The National Electrical Code provides detailed requirements for load balancing in three-phase systems. It's important to follow these requirements to ensure the safe and efficient operation of the electrical system. Overcurrent protection is an essential safety feature in any electrical system. It is designed to protect the wiring and equipment from damage caused by overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to automatically interrupt the flow of current when it exceeds a safe level. Circuit breakers are reusable devices that can be reset after they trip. Fuses are one-time devices that must be replaced after they blow. The National Electrical Code provides detailed requirements for overcurrent protection in electrical systems. It's important to follow these requirements to ensure the safety of the electrical system. Grounding is another essential safety feature in any electrical system. It is designed to provide a low impedance path for fault currents to return to the source, tripping the overcurrent protection device and preventing electrical shock. Grounding is typically achieved by connecting the metal enclosures of electrical equipment to a grounding electrode, such as a ground rod or a water pipe. The National Electrical Code provides detailed requirements for grounding in electrical systems. It's important to follow these requirements to ensure the safety of the electrical system. The proper installation and maintenance of electrical systems are crucial for ensuring safety and reliability. Improperly installed or maintained electrical systems can pose a significant risk of electrical shock, fire, and equipment damage. It's important to hire a qualified electrician to perform electrical work. Qualified electricians have the training and experience necessary to safely and effectively install and maintain electrical systems. It's also important to regularly inspect and maintain electrical systems to identify and correct any potential problems. Regular maintenance can help to prevent electrical hazards and extend the life of the electrical system. The National Electrical Code provides detailed requirements for the installation and maintenance of electrical systems. It's important to follow these requirements to ensure the safety and reliability of the electrical system. In conclusion, the use of the high leg in a high leg delta service for 240 volts appliances by combining it with a 120 volts phase is a violation of the National Electrical Code and poses significant safety risks. It's crucial to adhere to the NEC guidelines and utilize the appropriate phase conductors for 240 volts loads to maintain a balanced and safe electrical system. The alternative is to use the 120 volts phases to get 240 volts for the appliances that need it.